Hi! So on Friday I will give a small workshop about Linux drivers at the Kieler Linuxtage, and I have to practice a little bit. So I thought, hey, when I have to practice it, why not just record it and put it on my YouTube channel so you can see it if you're interested but cannot join my presentation. So here I want to welcome you to my Linux Driver workshop. This should give you an introduction to Linux Driver Programming. Maybe first some words about me. So my name is Johannes Reuth. I run an embedded Linux YouTube channel where I'm focusing on how to write drivers for Linux, but I'm also doing other stuff like user space programming or how to access various interfaces on Linux. Okay, so here is our agenda. So the goal of this workshop is for you to be able to program a small driver for a Raspberry Pi. But before we can do so, we need some theory. So the first 3 bullet points are just theory. After this theory, we can start and write our first Hello World Linux kernel module. And for compilation, we will need a makefile, so we will write this as well. Then I will show you how to manage modules with the bash, so you're able to load the module and unload the module. Then we will be talking about the device tree and device tree overlays. And last but not least, we will take a look at 2 subsystems, so I'm quite sure I will manage to be able to show you the I2C Subsystem, and if we have some time left we will also check out the Industrial IO Subsytem. So let's start. First, let's talk a little bit about what is the Linux kernel. So basically, because of the Linux kernel, you can use any Linux PC kind of in the same way. And it doesn't matter which processor you have, how much memory you have, or what kind of mass storage you have, or what kind of hardware you have attached to it. Let me give you an example. If you store a file in your home directory, you don't know if it will be saved on an SSD or on hard drive or maybe on net storage. This is all taken care of by the kernel. Another thing the kernel does is it enables you to run multiple processes even on a single core CPU. So the kernel is responsible for time scheduling and for giving every program a slice of time in which it will be executed. It's also responsible for memory management and make sure that every process gets its own memory view. And it's also there for accessing the hardware, and therefore we have drivers. So the Linux kernel itself is a monolithic kernel. This means the kernel itself is one binary program which is run, but this would mean every driver would have to be baked into it. And for example, if you're running a PC with an AMD GPU, you don't need the drivers for NVIDIA or for Intel graphic cards loaded into your system. And this is why we have this loadable modules. So this will make our kernel a little bit smaller. And with a device manager, we only load the modules into the kernel, which we really need. And in this workshop, we will only focus on how to write loadable modules. So at the end, we will get files called kernel objects or KO files. And these are files which can be loaded into the kernel. But after they are loaded into the kernel, they are part of this big kernel binary program. And how can the user space access functions from the kernel? Well, this is done via system calls. And popular system calls are open, close, read, write, maybe even IO control. And because on Linux everything is a file, you can do a lot with only these system calls here. Okay, so much for Linux kernel. Let's take a look let's take a look at the differences between user space programming and kernel space programming. So here I have made up a small table showing you the main differences. First, let's talk about resource access or memory access. So a user space program has its own view of the memory, and this view is given by the kernel. So this means you have restricted access and it requires permissions to access something. For example, if you have one user space application running and you want to interact with another user space program, you can't directly access the other program's memory. On the kernel, we have a monolithic kernel, so everything is one big program. There you have unrestricted access. And for example, from one driver, you can mess up with the memory of another driver. So this makes it a little bit more dangerous. So you have to watch out not to mess around with things you're not interested in, because then you could break the system. But of course, having unrestricted access also comes with more power and more abilities to write programs, for example. Now let's talk about hardware access. So if you want to access the hardware from a user space program, normally this is only possible over a driver. But if you're in a kernel module, you have direct access to the hardware. How to start a program? Well, on the user space, you have to start it, for example, by typing /program, and then you run the program. On a kernel module or on a driver, you have two possibilities. One possibility is the driver is directly baked into your kernel, then it's starting automatically when the kernel starts. Or the other option is you have a loadable kernel object, which we will have here in our workshop. And in this case, we have to load the module into the kernel, and then the driver is loaded and starts. Now let's talk about latencies. On user space programs, in order to access the hardware, we need to use syscalls. And by using syscalls, we will get a higher latency. In a kernel module, we can directly access the hardware, so we have lower latencies. And maybe I will give you another example. So maybe you know the PCF8574 chip. So this is I2C to GPIO expander. So here we have I2C, and then over this chip we can control up to 8 digital inputs and outputs. So for this chip, if you want to program it, it is possible to write a user space program directly or access I2C over some syscalls and then controlling the pins here like you want to do them. But if you are using a driver module instead, you can there is a framework in the driver called GPIO chip. And if you write a driver which is compatible to this GPIO chip implementation, then you can use the GPIO tools such as GPIO set and get to access the GPIOs. The advantage is if you're using the driver, you can just use these tools and you don't have to know you're actually accessing the I2C bus. So, for example, you can use the same commands for an USB to GPIO expander, for example. So the driver will give you an abstraction of the hardware, and you don't have to know how the access really works. So this is something the kernel takes care of you. But in some cases, it's also absolutely valid to write a user space program if the device is quite simple, for example. Okay, so what we will do here in this workshop is we will write a driver, or we will do our Linux kernel programming on a Raspberry Pi. And here we have to know the Raspberry Pi is using an ARM architecture. But on our laptops, we normally have an x86 architecture with a processor from Intel or AMD. So if we would compile the kernel with our native installed GCC, the output binary will be compiled for x86, and the Raspberry Pi can't do anything with it because it doesn't understand this instruction set. So to compile a kernel module for the Raspberry Pi, we have two options. The first option is to use cross-compiling. And cross-compiling is we are on the x86 program, but we are producing code for an ARM processor. But I decided not to do this because using cross-compiling is a little bit difficult and it requires some setup. So you have to set up your compiler first, and this can be a little bit tricky. So as the Raspberry Pi is a quite powerful single-board Linux computer, I thought, okay, let's directly compile our kernel module on the Raspberry Pi. In order to do so, I had to prepare the Raspberry Pi a little bit, and you can see the instructions how to do this here. I won't go over all of them, but this one here is important. So with this command, I'm installing the Raspberry Pi kernel headers. The kernel headers contain everything I need to be able to compile the Linux kernel. So here we have all the header files which are needed for the Linux kernel, but also the make files and stuff like that. Okay, now we finally made it to our first Linux kernel module. So the Linux kernel is written in C, but nowadays with later kernels you also have the ability to use Rust to build at least your kernel modules. And here you can see a structure for a simple Hello World kernel. But even if it's a C program, it looks a little bit other than a user space program. For example, we don't have a main in here. Instead, we have an init and an exit function. Because you have to know, these kernel modules will be started after they are loaded into the Linux kernel. And after they are loaded into the Linux kernel, they will execute an init function. If we remove them from the Linux kernel again, then they will execute an exit function. So down here with this parameters module init, we are defining which function should be our init function. And in here we are saying this, my init up here is the init function. And with module exit, we tell the module which function we want to call when the module is removed. And this is my exit, which is up here. Then we have to define the functions. So for the init function, it needs the return value int. On success, we are returning a 0, so if loading worked, but in case of an error, we can return an error code as well to indicate why the module failed loading. With this, macro here, this is just to make it a little bit more readable, and this is telling us the next function will be the init function. Then we can choose any name. I choose my init here, and the function doesn't need any arguments, so void here. Then what we're doing in this function is we are calling printk. Hey, this sounds a little bit familiar. From user space programming I know printf. So the problem is here in a kernel module you don't have the standard output. All you have is the kernel's log. So the kernel is logging itself over a log file, and to add a new line into this log file you can use the function printk, which works quite similar to printf. And here I'm writing to the kernel's log hello kernel, and that's it. And then I'm returning 0 to indicate the module was loaded successfully. The exit function has to be from the type void, so no return value, and void, also no arguments. This under exit is just a macro to indicate, okay, this is an exit function. And all we're doing here in this exit function is we're printing another line to the kernel, in this case, goodbye kernel. Then here we are setting up some module data. We need least this parameter here, the module license. And here we are setting the license to GPL. Why do we need this? Well, some GNU Linux distributions only accepts or only will load drivers which are free and open source software, and therefore the license must be known to the module, and this is what we're doing with this module license macro. Then I will set up some more information with module author. I can give an author of the kernel module, a module description. I can add a small description to it. And to have all these macros and functions here available, we have to include the files linux/module.h and linux/init.h. And that's basically all we're doing here in this simple Hello World Linux kernel module. Okay, now we have the source code for our Hello World Linux kernel module, and we're saving it under hello_kernel.c. But how we can compile it? Well, to compile the Linux kernel, we will use makefiles. So here I'm in the source code of a Linux kernel, and if I do an ls here, you can see here we have a makefile in here over which we can build the whole Linux kernel. And if we have installed our kernel headers, we are also able to find them under lib modules, then the number of the kernel, and build. So in here we have about the same structure, and we also have a makefile in order to build our kernel modules. So this is our makefile we will use to compile this Linux kernel module. This variable here, object m, is quite important. So if you have a driver and you have three options which you can do with this driver. The first option is you can compile this module directly into the Linux kernel. In this case, you would add your object file to object -yes, I think. This will go directly into kernel. Then you have the option to compile your driver as a standalone Linux kernel module or a KO file. In this case, you have to add it to object -m, and this is exactly what we're doing. So here we're adding hello kernel.o. O stands for compiled but not linked object file, and this file here, hello kernel.o, is produced by compiling hello kernel.c, but not linking it. And the last option is you don't want to include the driver at all in your build of your Linux kernel. In this case, you don't have to add it to any variable here. The next thing is we're defining two targets here, two makefile targets. The first target will be called directly if we just run the make command. So here in this default command, we are calling the makefile, which is stored under lib modules, and then uname.r will give us the string of our current kernel version, and then the build folder. So if I go back here, and if I list lib modules, and then execute uname -r build. Okay, this is odd. Modules. I've updated my system. This is why this doesn't match currently, but normally uname -r would give us our kernel path. So this here will just land into this folder here, and in which we have this makefile. So basically we're calling this makefile in here, and then we're setting the capital M variable. This means please search for kernel modules in the following folder, and this pvd is just the current path we are in, so the path of our current folder, and then we want to call the target modules to build all loadable kernel modules. And then we have to be able to clean up our kernel build too, and this can be done over the clean target. So here in the clean target, we are calling the exact same makefile. We are passing our current folder as the folder in which it should perform the clean, and then we're calling the target clean to delete all the created or compiled files. And that's basically it. Okay, so at the end, after the compilation, we will get hello _kernel.ko file. But what can we do with it? Well, in order to load this module to the kernel, we will use insmod for insert module and the name of the module, and this will load the module into the kernel. To remove the module from the kernel, we will use the rmmod program and giving it again the name of our kernel module. If we want to see the kernel's log, we can use dmessage, and if we want to see which modules are currently loaded, we can use lsmod. If we want to get some information about a kernel module, we can use modinfo, for example. And last but not least, if a module is under lib modules and the name of the current kernel, we can use modprobe module name to load the module name, including all its dependencies. But therefore it must be in this specific folder, so we in our workshop will only use insmod here most of the time. Okay, now with this knowledge, we can finally do our first assignment. So please compile the simple Hello World kernel module on your own Raspberry Pi, and then we will continue. Okay, so now let's try to fulfill the first assignment. So our task is to program a simple Hello World kernel module here on our Raspberry Pi 0 in this case. Okay, therefore the first thing we need to do is we have to connect to it. So let me go to my Ethernet settings. This is my Raspberry Pi Pico. Let's configure it. I want to have a manual IP address because I've set a static IP address in here, and there should be the IP address of my PC. Now we should be connected. Okay. And if we open up a terminal in here and run nmap sn 192.168.123.0 and subnet mask 24 bits, we see we have two participants here on this network, and this here is the IP address of my Raspberry Pi. Next thing I will do is I will create a new folder here. In my home directory I will call Pi, and then I will use SSHFS to mount this. So I will mount user at the IP address of my Raspberry Pi and the home folder into my local Pi folder here. I have to save the fingerprint, I have to give it the password, and now it's done. And if I take a look into Pi, we can see it's empty. But if I touch a file in Pi and then I SSH to it, take a look at it, we can see the file is here. Okay, so now the next thing we have to do is we have to program a small Hello World Linux kernel module. So I will create a new folder, I will call hello, I will go into this folder, and then let's do hello kernel.c. First we need some includes. So we have to give it a license, and then yes, and maybe also an author. And the description. Then we need, so on Linux kernels we use the static here quite recently, so this function is only available in this kernel module and nowhere else. Okay, it seems set syntax or syntax. Okay, we can just copy these 3 lines here. And this should be goodbye kernel. And then we need module init, my init, and module exit, my exit. And that should be it. Now, next thing we need is a makefile. So we will add hello kernel.o to the object m variable. Then we will need an all target. We will call the makefile in lib modules shall uname r build. We want to add our current folder to the path in which it's looking for kernel modules, and we want to use the target module here. And then we need the same for clean, but instead of modules I will call clean here. Okay, then let's try to build it. Let's run make. Okay. Let's see where I made a mistake. Ah, yes, I forgot a $sign. That should do it. Okay, so now it's building the kernel module. But yeah, I made a mistake here. I built it on my local computer. First I have to yes, $sign too much. Okay, and now let me SSH to my Raspberry Pi again. CD into hello, and let's run make there. This will take a little longer because the Raspberry Pi is by far not so powerful as my desktop PC I'm using here for the recording. So this will take a little while. Almost done. Okay, so let's run mod info. Hello. Okay. Okay. So we can see here this is our loadable kernel module, and if we run mod info and this kernel module here, we see this is a simple Hello World Linux kernel module, the author and the license. Here we can see for which kernel it was compiled. And let me open up a second window. And let me SSH to my target again. And here I will run sudo dmessage -v. So this should follow the Linux kernel's log. And now if I use insmod to load my Hello World kernel module, you can see here we got this new line here, hello kernel, hello kernel. And if I remove the module with rmmod, or first let's check all the loaded modules. And in here somewhere we should see our hello kernel module. And to remove it, I will call rmmod hello kernel. And now it will print goodbye kernel to the kernel's log. Okay, so this was the first assignment. Let's continue. Okay, so now let's take a look at the device tree. So what is the device tree and why do we need it? Well, therefore you have to know ARM or, for example, OpenRISC-V systems do not have an automatical hardware detection mechanism like we have on x86 systems. So on x86, normally at boot time we have UEFI or BIOS, and this will search for all the available devices. For example, which amount of memory is available, what type of memory it is, which timing parameters it has, and which other devices are connected to the system. And then it will pass all this information over ACPI tables to the Linux kernel, and then the Linux kernel knows which devices are there. But on ARM-based systems, we don't have something like that. But the Linux kernel needs information about which devices and which hardware is available. And the device tree provides this type of information. So the device tree itself summarizes all the available devices in a tree-based structure. So the device tree is a binary, needs to be a compiled binary file, the device tree binary, or like we have it here, DTB file. And to compile this, we need a human readable form, and this is device tree source or device tree source include. So for the device tree, we can have include files. I will show you this, maybe I can show you this just in a second, how to use this device tree include files. And here, this device tree source file describes how our system is built up. It starts from a root, and then all the devices are there in a hierarchical order. So if you want to check out the device tree, it's available under proc device tree. So here I'm connected to my Raspberry Pi. So let's take a look at proc device tree. And in here we can see our device tree, or a second way to access it is to go under in this directory, sys firmware device tree base. Firmware device tree base. Okay. But how can we get a human readable form from this folder structure? Well, we can use the device tree compiler, the DTC, to compile or to extract a device tree source file from this device tree folder. So the way we are doing this is DTC. Our input file format with a capital I is FS file system, I guess. Yes. Our output format should be device tree source. Then we can we say please take the device tree from sys firmware device tree base and please put it in the file my device tree.dts. Okay, done. Let's take a look at it. Sadly, here I just have VI available, but no matter. But here I have a better Vim available. So let me open it up. So this is the device tree. So here we have our version tag, and here we have our root. So this is our root, and down here we can see all the available devices. So here we have some parameters. For example, the model here is Raspberry Pi 0 revision 1.1, and here we even have a serial number here. And for example, here we have a device clocks, and this will give us the available clock frequencies and the oscillator. So here we have the general oscillator, and here we can see the frequency, and down here we have the clock for the USB. This memory is quite interesting too, because this memory describes how much memory is available at the device. And here, so the memory is available at physical address 00, and it has a size of this hexadecimal value. So maybe if I'm running ahead 50 lines of my device tree, and if I check how much megabyte this is, therefore I have to divide it by 2024 two times, and then you will see we have 484 megabytes available. This is about the 512 megabytes which are assembled on the Raspberry Pi. Okay, let's take a look at the device tree again. So we have the memory in here, and so we can see all the devices. Here we can also see, okay, we have, for example, let's search for LEDs. So, to see the LEDs. Act. Yes. So here, for example, we're adding a device LED. This device is basically this activity LED we have here. And this compatible string, we will take a look in just in a second, but basically this compatible string tells us which driver is or has to be used for this device. In this case, it's GPIOs minus LEDs. And here we are adding the activity LED. This is the number of the LED, the label as active or activity here. The default state is off, and the trigger is active power here, for example. And this way, various devices are described. For example, up here we can see the our SPI. Our SPI bus is described here. Maybe here we can see our USB device which is available. This thing here is the physical address. So this here is the physical address at which the USB IP or the registers for the USB IP can be found. And this way the device tree describes all the available devices. Okay, and we could take this device tree source file and compile it into a device tree binary. And if we want to add a device, we could use it, search for the device, and then add it. For example, if we want to add a second LED, where is it? Yes, here we could create a new LED, my LED for example, and then just fill in the required parameters. But then we would have to recompile the whole device tree. And sometimes it's more useful to use a device tree overlay. This way we can just add one device and don't need to recompile the whole device tree. And device tree overlays normally, after they are compiled, have the ending DTBO for O for overlay. Let's take a look how a device tree overlay could look like. So up here, you know this is just the version of the device tree. And this is a plugin or an overlay. And we have here our root, the root of the device tree. Here we're adding a fragment. The target is I2C1, so we want to add a new device to I2C1. And down here we have the overlay. This hash always means number of. So the number of address cells is 1 dword. The size cells are 0 dwords. So for example, if you remember the memory, we had something like 0x0 and then we had a value. And here the first parameter is the address. This could even be a physical address, or for I2C it's the I2C address. And the second argument here was the size. If we would have size of address cells would be 2, or number of address cells is 2 and number of size cells is 2 also. This would look like something like this. Then these two are the address, and then we have a second set which would be the size. This would be the size. This is the address. So this is how it works. But for I2C, we just have to specify the I2C address, which we are doing here. So the device we want to add has this I2C address. The name of the device here is myADC, and we are and this at 10 also indicates the address. So the address here once again is hexadecimal 10. This compatible string is important because over this we can tell the device which driver to use. In this case, this is compatible with the driver brightlight, myADC. And normally this is spelled the following way. The first one is the vendor of the device or the driver, or which produced the driver, and the second one is a device name. So here the company would be Brightlight and the device name would be my device. You see something like this, for example, NXP PCF 7584 would be the compatible driver for the I2C 2GPIO bridge. And this status is okay, indicates the device is active. If we would set the status to disabled, the device would be disabled. And this can be used, for example, if you want to disable any device, you can use an overlay, set the target, and then just write status is equals disabled, and then the device would be disabled. One important thing here is to mention is you need the semicolons to end each lines. And when you open up a brace, you have to close it, and then you have to add a semicolon. And this is our overlay. This we could save as testoverlay.tts, and in order to compile it, we will use the device tree compiler again. So our input format is device tree source, our output format would be device tree binary, and the name of the output will be testoverlay.dtbo, and this way we can compile it. Okay, cool. Now let's take a look at the I2C subsystem. First, does everybody know what I2C is? In case not, I will explain it briefly. So I2C is a 2-wire bus. You have a SCL clock line and you have an SDA data line. Then on this bus you have our Raspberry Pi, and this will act as a master. So the Raspberry Pi initiates the transfers. And then you have some devices which answer to the to the transfers initiated by the Raspberry Pi Pico. To identify a device on this bus, every device needs to have a unique 7-bit address. So let's say this is 17 and this is 33, for example. And on I2C we can do two operations. We can do a write. So the master can say, hey, I want to write to slave with the number or address 17, or the master can read from the desired slave. And that's all the operations which are available on I2C. So this is I2C in a nutshell. So how can you write a Linux driver for an I2C device? Well, you have to follow the following steps. First, you have to name the compatible device or the device for which you want to write a driver for. Then you have to implement a probe and a remove function. The probe function will be called when a device is detected. The remove function will be called when the device is removed. For example, with a USB device, probe will be called when you plug in the USB device, and if you remove the USB device, the remove function will be called. Then you have to create a driver struct which will contain probe and remove and the compatible devices. And last but not least, in the init function you have to add the driver to the kernel, and in the remove function you have to remove the driver from the kernel. So let's take a look at it, how this is done. First you have to know, or first for using function for I2C you have to include linux/I2C.h. Then you need to know there are multiple ways to add I2C devices. One way is to do it over a device tree overlay or over the device tree, which we will be doing. And another way is, for example, when here on my laptop, if you go under sys bus I2C, we have this devices folder, and I can select a bus, for example I2C 0, and in here we have a file called new device, and if you will echo an address, I think, and the name of the device into this new file here, it would add the device myADC with this address. Here it will search for driver, and if it's able to find a driver, it will load it. So these are the two mechanisms we have for adding I2C devices. So we will use this mechanism up here, so you don't need to include this in your sample driver. But I will explain both. So what we are doing here is we are creating a table of off-device IDs. OF stands for open firmware, and the device tree was inspired by open firmware, and so if you see OF, this means the device tree. And here we are declaring an array of off-device IDs. So every off-device ID stands for one compatible device. So our first one has the compatible string bright light myADC. What we could also do is we could add some driver data here with .data and then my data. Okay, so this is one device we add. If our driver is compatible with multiple devices, we will have a second entry here with compatible, then the string again, and optional the data. And to indicate this list of compatible devices is AND, we need this empty brace. So this indicates the end of the list. With this macro module device table, we make our device table known to the user space. And now the user space or device manager knows, okay, if a device tree overlay is loaded with this compatible string here, I have to use this driver here. Okay? And the second way I've shown you how to add devices would be over the sysfs. In this case, I would need a table of I2C device IDs. And once again, you can see here, first we have a string, and then we can pass driver data, but this is optional. At the end, we will need this empty braces to indicate the end of the list. And if we want to add a driver over this way, what we would have to do is exactly echo I think, new device. Then it will look in the tables if it can find the string my device, which is exactly this string here. And if it can find the string in one of the tables, it will use this driver to load to load the device. Okay. But as I already told you, you don't need this because we will use the device tree method to add devices to our Raspberry Pi 0 or Raspberry Pi. Okay, next slide please. Then we have named the compatible devices. Now we have to implement a probe and a remove function. The remove function has the return value int. In case a device was probed successfully, we will return 0, otherwise an error code. We have two arguments here. We have this struct I2C client, and this is a pointer over which we can access our I2C device. And the second argument is a pointer from the type struct I2C device ID. And if we are using the sysfs way to add devices, this pointer will point to our current entry. But as we're using the device tree, we don't have to use this pointer here. So over this we could access the driver data, for example. Okay, and then the remove function is from the type void, and it has as an argument a pointer to our I2C device, and that's it. Okay, next thing we need to do is we have to create a driver struct. So this struct needs to contain a probe function, which is called when we are probing the device, a remove function, which is called when we are removing a device. This ID table is something we don't need as we are loading the driver over the device tree. But if you want to include it, you can include it. And down here, we are saying the name of the driver here is foo, and the device tree match table is this foo of IDs, which we have declared up there. Now the last thing we have to do is we have to register this driver. This can be done with I2C add driver, and then we have to pass a pointer to our driver struct. In order to remove the driver again, we have to call I2C delete driver and a pointer to our driver struct. And a cool thing, normally, so if our init and exit function only consists of these two function calls, we can use this macro here. This macro will create this structure for us automatically. So module I2C driver foo driver will create an init and an exit function for our current driver and will make everything look a little bit more nicer. Okay, so let's talk about some other useful functions for I2C. So if you want to read a byte from I2C, we can use I2C as mbus read byte. And here we have to pass in a pointer to our I2C device from which we want to read. And the return value is the byte we have read. Then if we want to write something, we can use the function I2C as mbus write byte. Pointer is, or the arguments are a pointer to our I2C device and the data we want to write. If we need a little bit of delay, we can use mdelay and pass in the time we want to wait in milliseconds. But in order to use this function, we need to include linux/delay.h. And the other functions are not needed for this for the next task, but I will go through them quickly. So you can set some data to an I2C device over the function I2C set client data. And here you have to pass in the pointer to the client you want to set the data and a pointer to the data you want to set. And this is useful if you need these data later. For example, if you are assign some data in the probe function and you want to use it in the remove function as well, you can use up here set driver data, and down here get driver data, and you will have the data back again. Okay, and last but not least, this function here, defm kalloc will allocate size bytes of memory for a specific device, and this GFP flag is an allocation flag. Normally we're using GFP kernel in here. And the cool thing about defm is if the device is removed, the memory will be automatically be freed again. And for example, with our client, what we have to do to get this device here is client.device. This way we'll get the device assigned to our I2C client here. Okay, cool. Then we're almost here for our next task. So I will give you a Raspberry Pi Pico, which is programmed to act as an I2C ADC, and you have to write a driver for it. So the Raspberry Pi Pico is set up for a test device. I have connected a variable resistor to an analog digital converter, and we can read out the value of this ADC over I2C. So a read access will return the ADC value as an 8-bit or a byte value, and in order to, and if we write to the device, we will, if we are writing a 1, the ADC is read out every 500 milliseconds, and if we write a 2 to it, the ADC is read out once. I will show you this just in a second. And here you can see the circuit diagram, how to connect your device to Raspberry Pi. Here I've made a mistake. Ground has to be connected to pin 3 and not to pin 2 here, but the rest is, yeah, correct. Some useful shell commands for handling or using I2C. If you want to scan the bus, you can see I2C detect -y1. If you want to read a byte, you can type I2C get y1 and the address from which you want to read. And if you want to write something, you can use I2C set and add here the value you want to write. And your task for now is you have to create a driver for the Raspberry Pi Pico I2C ADC. In the probe function, an ADC conversion has to be triggered by writing a 2, and then the result has to be read out and displayed in the kernel's log. You also have to create a device tree overlay for our Raspberry Pi Pico I2C ADC, and you can compile the device tree overlay and load it with DT overlay and the name of the overlay, and last but not least, you have to test your driver. So, have fun with this exercise. Okay, so let's try to fill this assignment. So the goal here is we have to write a driver for our Raspberry Pi Pico I2C ADC. So here you can see I have connected the Raspberry Pi Pico to my Raspberry Pi Zero, and I have connected this POTI to it. And here I'm connected to my Raspberry Pi. If I write or run I2C detect y1, I scan the first bus, and here I have a device present. And this is my Raspberry Pi Pico ADC. So what I already know is the I2C address for my overlay is 17 hexadecimal. And if I read from the device, I'm getting a 0. Now if I use I2C set and writing a 2 to this device and read it, I can get the current ADC's state. But if I rotate the knob here a little bit and read again, the value doesn't change. But if I write a 2 here again and read again, I will get a different value. And if I'm writing a 1 instead, and let's run an endless loop here, I2C get, sleep, done. And now I'm turning the knob, you can see the value is changing, so the value is now updated every 500 milliseconds. Okay, now we need to write a driver for this. So once again, I will SSH, I will mount /temp to my local P folder here. So here I'm connected to Raspberry Pi Pico's temp folder, and in here I will create a new file I will call my ADC. Let me change into it, and in here I can write the source code for my driver. So the first thing I need is a device tree overlay, and I will call it my ADC.dts. Yep, here we are. Okay, so the first thing I need is I need to specify the version. So let me go up here and check. Let's check how to do this. DTS minus version 1. DTS minus 1. That's it. And this is a plugin. Okay. So let's start at the root path here, and what I want to do, I have here a fragment at 0, I guess. Yes. And I have to close the brace here. So the target is I2C1, so the node I2C1. And then here I will have an overlay. So to I2C1 I want to add the device my ADC. Oh, first I have to specify the address, the number of address cells. This will be 1. And the number of size cells, which will be 0. Okay. Now I will add my device my ADC, and I will add it at, I will call it my ADC, and the address is 17 hexadecimal. So first I will write the compatible, or just compatible, the compatible string. Okay, no point at the start. Compatible is bright light my ADC. Let's take this. Oh, it should be my. Okay. Then the address is 70 hexadecimal. Status is equal to OK, so the device is enabled, and I think that was it. Okay, so let me try to compile this device tree overlay and make sure we haven't forgot any semicolon. So our input form is device tree source, our output form is device tree binary, then the output should be my adc.dtpo and the input is my device tree. Oh yeah, first of course I have to SSH to my system. Let's do this. Let's navigate into temp my ADC. Okay, please respond. Okay, so in here we have our device tree overlay, and now we can call the compiler in order to compile it. Oh, this is a little bit laggy. Yes, here we are. Oh, okay, number, address, cells. Okay, we have an error here. Let me open up a second window. cd p my ADC with my ADC.dts, and let's check if I made something wrong. Number, address, oh, minus cells, not under cells. This can be the error. Let's run the compilation process again. Now it's looking good, and with sudo dt overlay I can apply my device tree overlay.dtpo. Done. And now our device tree overlay is present. And if we look under proc, device tree I2C, I think it's sock I2C at, I need to get the number, detect. Okay, one is at this address. I2C. So that's the address I'm interested in. Wait. Come on. We have here our my ADC device at address number 17. And with this knowledge, we can now start implementing the driver. Oh, come on. Okay. My adc.c will be the driver. First, I will include module /init.h. Oh, linux.init. Done Linux module and Linux I2C. Then let's module license will be GPL. Will be me and description. Driver for me RP Pico ADC. Okay. So now the first thing we have to do is we have to name the compatible devices. Oop, a little bit too far. Here we are. So we need to add a device table here. So basically this here. So let's do it. Static struct of device ID, and I will call it my ADC of IDs. This is an array. And in here we have one element. So compatible is, and now let's get the array directly from this file here, because this must be exactly what's in here. Okay, and then we have to end this with an empty brace to indicate the end of the list, and with module device table, this goes to the open firmware, so to the device tree, and we want to add my ADC of IDs here. Okay, so that's what we did here. Then the next thing is we have to implement a probe and a remove function. Module device table. So let's do this. My ADC probe struct I2C device or I2C client. I will call this client, and then construct I2C device ID. I will call ID here. So this is the function. Okay, and yeah, at the end I will return a 0. And what do I have to do here? So basically we want to first, let me add a print k here, ADC probe function, and then I have to tweak my Vim config a little bit someday. Never mind. Okay, and then next thing we want to do is we want to start one conversion, and then we want to read back the result. So how can we do this? Well, we need I2C SMBus write byte. We want to write to the client, and we want to write a 2 to start one conversion. Then we need delay ms, and we have to wait at least 500 milliseconds for the conversion to be over. Okay, mdelay is the name of the function. Delay. And in order to use mdelay, we have to include Linux / delay.h. Delay. And now let's print the result out to the kernel's log. Value, and this will be I2C SMBus read byte, and we want to read this from the client. And that's it. Then the last thing we need is an empty remove function. This only has one argument. And now, last thing we need to do is we have to set up our driver struct. So static struct I2C device I2C driver my ADC driver. So for probe, please use my ADC probe. For remove, use my ADC remove. Okay, then we don't have ID table, so we can skip this. Driver. Name will be my ADC. And of IDs, I think, of match table is foo my ADC of IDs. And that should be it. Now the last thing we have to do is we have to add our driver to the kernel, and this can be done with this module I2C driver macro driver, and here we have to pass in my ADC driver. Okay, so let me try to compile it, but first I need to write a small makefile for this. So my adc.o all make c lib modules shall uname r build ms pvd, and target is modules. Let's copy this, let's add the target clean, and at the end let's call clean. Okay, then we have to go back here. Now we have here our two files. Come on. And if the terminal is ready, we can run make. Let's see how much mistakes I've done. compilation will take a little bit of time because it's slow. Okay, no return statement in function returning non-void. Okay, my ADC 29, my ADC remove. Okay, let's take a look at it. Yes, here I have a typo, a copy error. This should be void, of course. Okay, let's try to recompile it. It's looking good. Okay, then let me open up a second terminal here and let me SSH to my Raspberry Pi. And here I will run dmessage -w to follow the kernel's log. I think I need to do this with sudo permissions. Okay, and now let's insert our module here, my ADCKO. Okay, we're in the probe function and the result was 136, which seems quite good. And if we remove it, yeah, we are in the remove function now. Okay, cool. So that was how to fulfill this assignment here for writing a simple driver for our I2C device. Let's continue and let's take a look at the Industrial IO Subsystem. Okay, now let's talk about the Industrial IO system. So IO stands for Industrial IO, and this is a framework which enables user space access for various types of sensors. For example, analog digital converters, temperature sensors, pressure sensors, accelerators, and so on and so forth. They are all bundled in this IO subsystem. The advantage of this subsystem is it standardized the interfaces for various sensors. And you can have access to the IIO over character devices, which you can find in /sys bus IIO. And the Industrial IO subsystem provides various functions for reading out the sensors. For example, you can read out the raw data, you can calibrate it, you can scale it, you can tweak some settings. For example, if you have a current sensor, on some current sensors you can set the shunt values and stuff like that. All of this can be done over the Industrial IO. So how to create a driver for an Industrial IO subsystem? First, you have to create a structure for an IIO device. Then you have to implement at least a read function. So this read function is just for our Raspberry Pi Pico ADC. And then you have to create a channel and an IIO info for this channel. So a device can have multiple channels. For example, if you have an ADC with different inputs, each input could be a channel, for example. And last but not least, you have to create the IIO device in your probe function. So let's take a look at it, how to do this. So first you need to set up a struct for your device. I have this foo struct here. One parameter of the struct could be a pointer to our I2C client, for example. Okay, and then we are implementing our function, our read function here. So the return value is integer, and here we are returning IIO val int if we could successfully read out a value. And the arguments, the first argument is our IIO device, so a pointer to our IIO device. The next argument is a pointer to the channel which we want to read out. The next is a pointer to the value, so in this pointer we can store the value. if we have a 64-bit value, we will have a val2 also available, and we will have a mask in here. So the first thing we are doing here is we are getting the data for our IO device by using this IO priv function, in which we are passing our device, and the return value will be a pointer to our device's struct. Then we are in this mask value, we can see the type of operation we want to perform, and in case the operation is IO gen info raw, then we have to read out the sensor and store the result in this value pointer here. So somewhere here we would set value, for example, if for our I2C device we could use I2C bus read byte, and then just pass our client in here, or our I2C client, and this way we could read out the value of our IDC and store it here in the client. In case the mask is something different to this operation, I will return error invalid, because only this operation is supported by our read function here, and if we could read out the value successfully, we will return IO value int. Okay, the next thing we have to do is we have to create the channels and the IO info struct. So here we are declaring an array of IO channel spec, an array, and the first argument here is, so the type is IO voltage because we have an ADC, and info mask separate, so our channel only supports the IO gen info raw, and other operations are not supported, but if they would, we could do an OR here and specify the operations. Okay, then here the info is, so, alright, yeah. Maybe let me store it somewhere else that this program is happy. Save as. Okay. And here in the info, struct, we can overload some operations, and we will only overload, or we will only set a callback for read raw. In case we want to perform a read raw on this device, we want to call the full read raw function, which I have shown you on the slide before. Okay. Oop. Wait. Okay. Give me a second. I'm back in a second. Okay, now we have all this information set up in the probe function. We have to create the IO device. Therefore, what we will do is, here I have declared our devices struct, ADC, and here I have our Industrial IO device. So with this function here, defm IO device alloc, I allocate memory for a new IO device. And in case this returns a 0 pointer, we are out of memory, so we're returning error no memory. But if this doesn't return 0, we have a new device. The first thing we will do is we will initialize our device pointer with IO priv, and as we haven't set the device yet, this will create us the memory for, or this will allocate the memory for our full devices struct. So here I will set the client field to the client, so I have a pointer to my I2C slave to be able to access it. And then let's go on. Then we have to set some stuff here. So here we are setting a name. In this case, we're setting the name from our, or we could also use module name here, for example, but here we are setting the name of our IO device. Here we are setting the info, or here we are setting the info struct, so this only contains our raw read raw function. The modes is in the IO direct mode, this is the mode which is supported. The channels is a pointer to our channels array, so here we have only one channel, and the number of channels here is 1, or array size of 2 channels, and this will return a 1 here. And now, in order to register our Industrial IO device, I have to call defm IO device register, and here again I have to specify the device for which I want to register this device, and then here I have to specify my IO device. And once again, this is a defm, so a manage function, so this device will be unregistered automatically when we are unloading the driver or when we remove the device from the device tree. Okay, cool. Now let's go to the final task. I would like to ask you to expand the driver so that the ADC can be read out over the Industrial IO Subsystem. Make sure you activate the permanent readout of the ADC in the probe function. Therefore, you have to write 1, so ADC value will be updated every 500 milliseconds. Okay, then the IO kernel module is needed for the driver. You can load it with this mobprobe command here. And after loading your driver, you should be able to read out the current state of the variable resistor over in voltage over this path here, and expand the device so that in the remove function the ADC is switched off. So this can be done by writing a 0 to the I2C device. So that's the next task, so have fun. Okay, let's do the last assignment, but first I forgot to mention something. So in order to use the IO subsystem, we need a header. We need the header include Linux IO/IO.h, and we need the header Linux include IO and sysofs.h. These are the two headers which we need. Okay, so now with this knowledge we can start with the assignment. And maybe, okay. So let's open up my ADC here and let's include the new headers. Linux/IO/IO.h and Linux/IO sysfs.h. Okay, so the first thing we need is a driver struct. So let's declare a new struct from the type myADC. And in this struct, all we need is a pointer to our I2C client. So yeah, that's it. That's all we need. Then the next thing is we have to implement the read function. So static int myADC read raw, and the arguments are struct IO device in the IO device, then struct IO channel spec const channel IO chan spec, struct IO chan spec const channel, then a pointer to the value, if it's more than 32 bits, and the mask. Okay, then I need a struct from the type myADC, and I will call it ADC, and this is IO priv to get back the private data of the IO device. Okay, so we could check if this is 0, but normally it should be okay. Then we have to check if the mask is equal to IO chan info raw. So if mask is equal to IO chan info raw, and in this case I will set well2 to 0 and well1 is equal to, or well is equal to I2C smbus read byte, and we want to read it from ADC client. and else we will return minus error invalid. But if we come so far, we will return IO well int. Okay, next thing we have to do is we have to set up the channels and the IO info struct. So this here, static construct IO chan spec foo channels, static construct IO chan spec back my ADC channels. This is an array, and this array only has one parameter. The type is IO voltage because we have an ADC, and info mask separate info mask separate is equal to bit, so we want to set the bit, and we only want to set this bit up here. And that's the only element in this array. Okay, good. Now we have to set the IO info. For my ADC info. And here we only want to overload read raw, and this should be equal to my ADC read raw. Read raw. Okay. And now, last but not least, we have to add the device here in the probe function. So let's do this. Struct IO def in the IO device, and we need struct my ADC pointer ADC, then is def mkalloc def mio device alloc, def mio device alloc. We want to bind it to client device. Size of struct IO device def, and that's it. In case this returns a 0 pointer, we will return error no memory, and if not, the creation was successful, and I can now allocate memory for the private data, and I can set ADC client to client. Okay. Now def name will be module name. Then we have info will be my ADC info. Then the modes will be IO direct mode. Modes IO direct mode. And channels will be my ADC channels, and number of channels is missing. Num channels will be array size of my channel's ADC. And last but not least, we have to register the device. So, okay, here we are writing a 2 to our I2C slave, so the ADC value is updated every 500 milliseconds, and then we will do defm IO register device register, and client device, and in the IO device, and that's it. And in the remove function, I want to stop the update, so I will write 0 to it. Okay, now let me see how much mistakes I've made here. So let me try to recompile the device, or the device driver. Okay, quite a bit of mistakes. So, okay, this is only bit, not bits. So, okay, here I have a typo. Okay, this must be a pointer. Yes. So, yeah, let's try to correct it. So, this here, of course, has to be a pointer. This here should be a minor. B. Then what else do we have? I think this module name was not something. Bit, instead of bit, it's bits, it's just bit, right? Bit, yeah. Bits, it's just bit, okay. And now let me try to recompile it. I think the last error is the module name. Let's see. Okay. Struct IO def. Module. My ADC info. From const IO info. Come on. Yes. IO info. IO info. Static construct. Static construct IO info. Let me stop the video for a second while I'm doing the trial. Good, I could find my error. So basically the error was here at the info. I had to pass a pointer, and that was the error. Okay, so now let me try to load this module. So I could compile it. Now let me try to load it. My KO. Unknown symbol. Ah, yeah. So I got an error here inserting this module. The reason for this is before I load this module, I have to load the Industrial IO submodule. And now I should be able to insert the module. And now if I look under sys bus IIO devices IIO device 0, I have here this in raw voltage, and if I cat from it, I should get the current value. So let me do a watch of the last command, so it's repeated every second. And now I will turn the the resistor a little bit. Okay, I hope I didn't killed it by this. Yeah. Okay, then we have still an error here. So first let me unload the module, my I2C. And if we take a look at the source files, maybe I'm writing a 2. Yeah, I'm writing a 2 here. I have to write a 1, so the value is updated every 500 milliseconds. So I think this was the error. Let me try to recompile it. And then we will load it again and we can see what's wrong or if it's working now. Okay, the compilation is done. Now let me try to insert the module, my I2C KO. And let's do the watch command again. And let's give it an interval of every second. So let's update it every second. And now if I turn the knob, you can see, yeah, the value is changing. Cool. So we have fulfilled this assignment. And that is the end of the workshop. I hope you've enjoyed it, no matter if you were on the workshop in present or if you have watched this video. So I guess that's for today. Thanks for watching and goodbye.